Hello class. Yesterday I sent out a Blackboard announcement to the material that is needed to be comprehended for understanding Chapter 6. And today I thought I would do a video on that material. So you've got the reading in the Blackboard announcement with each concept bulleted and what you need to understand about it. And today I'm going to make a video. Now, also on that last Blackboard announcement, there are videos attached. Those are important to watch. They show how to do orbital diagrams, how to start electron configurations. They also discuss the quantum numbers, N, L, ML, and MS. So it's important that you watch those videos and understand what's being talked about. Don't just skim them. Watch them a number of times in order to understand the concepts of quantum numbers and then how they build the electron configurations. So this video is from the photoelectric effect up until the quantum numbers. And again, it's what was bulleted, but I think that it'd be also good to hear a discussion on this. I hope you are watching the videos. I think they're important, and that's how we supplement, or that is a requirement for the class in a hybrid type system during this pandemic. If you have questions, make sure you email me and or schedule an office hour and we can go over particular points. So the last time we were talking about the photoelectric effect, and the importance of the photoelectric effect is Einstein proves that Planck is correct in his theory that states that E equals h nu. And so again, what we have here is most people believe light is a particle, or some people believe it's a wave. And Einstein treats this as a particle, and he calls it a photon, and it has a certain frequency. And he notices that when he increases the frequency, that electrons are ejected from this plate and they travel over here to this rod. Below that frequency, below the threshold frequency, he sees no current detected. So there's a gap between here and here, and the electrons have to traverse that gap in order to complete the circuit. So if the electrons are not being ejected, then the current is zero. But once we increase the frequency to the threshold frequency and above, we see electrons being ejected from one plate and traveling to the rod, completing the circuit. And he noticed that whether a current is detected or not is not based on intensity of the light, how bright it is, but the frequency. So he shows a direct relationship between frequency and energy. So he proves that Planck is not crazy, that his equation does apply. So again, Einstein made an assumption. He suggested that the beam of light is really a stream of particles he called photons. And using Planck's quantum theory of radiation, E equals h nu, as a starting point, he states that the energy of the photon must equal Planck's constant times the frequency of the light. And again, when we talk about light, we're talking about radiation, and we are talking about visible radiation, but just keep that in mind as we're going through these slides. So Einstein thinks this through. He says, okay, well, the amount of energy required to knock the electron off of the piece of metal is called the binding energy. And then the kinetic energy is the amount of energy required to have the electron travel from the piece of metal to the rod over there. So This is positive and this is negatively charged. And to get this to travel, it has to have a kinetic energy. And if we add those two energies together, it must equal h nu, the Planck's constant times the frequency. So you need to know this equation. You may have calculations involved. There's different scenarios here. Maybe you have to calculate the kinetic energy. Maybe you have to calculate the binding energy. Just remember that energy is usually in joules. It can also be in kilojoules. These are both units of joules. And then you also have, they can be kilojoules per mole. So something you may want to keep in the back, keep on paper, is 1 mole is equal to Avogadro's number. Now, we haven't formally talked about this in class. We will. And this book assumes that we have, because we went from chapter 2 to chapter 6. So 1 mole of anything, 1 mole of eggs, 1 mole of atoms is equal to Avogadro's number of particles or atoms. So if you have 1 mole of atoms, you have 6.022 times 10 to the 23rd atoms. So 1 mole of atoms, a mole just means Avogadro's number there. So what kind of problems can you expect? Well, a photon has a wavelength of 5 times 10 to the 4th nanometers in the infrared region. A photon with a wavelength of 52 nanometers is in the ultraviolet region. Calculate the kinetic energy of an electron ejected by the photon in part B from a metal with a binding energy of 3.7 electron volts. All right, so for the first one, they just want us to calculate the energy. Well, we know this. E equals h nu. And here's a substitution. H, and then for nu, we're going to put in the speed of light divided by the wavelength. All right, because we learned previously that the speed of any wave is equal to its wavelength times its frequency. So we want to solve for, since we're given the wavelength, we want to solve for frequency. So we divide both sides of this equation by wavelength. And then we substitute that in for frequency there. So that's how you're going to do the first 2 parts. And you're going to find that the shorter the wavelength, the higher the energy. Okay? And then for the last one, this is where it becomes important that you have h nu equals the kinetic energy plus the binding energy. Now we were given the binding energy, and we have to determine the kinetic energy, and we have actually calculated this part for the 52 nanometers. So once you calculate part B here, how much energy this is, you will plug that in for this value, and then you'll solve for the kinetic energy. Now, you're looking at this problem, you're going, well, we haven't talked about electron volts. What's the relationship between electron volts and joules? Well, let's look at that. So we have talked about, and there's a typo here, we have talked about that a coulomb is 1.602 times 10 to the negative 19th joules. That are coulombs. Let me do this again. 1 electron has a coulombic charge of 1.602 times 10 to the negative 19th. Now, this actual relationship is in your endnotes or your book. On the chapter ends, they have a bunch of conversions and or equalities, and that's actually one of them. Now, I'm not going to ask you to memorize this. I would give you this on a problem. It's not that important to me at this point. This would be something you will have in your physics class. So it's a nice introduction, but I'm not requiring you to memorize this conversion. I will give you this conversion. But the key is since everything is working in joules or kilojoules, make sure you're working with joules and not electron volts. So that's why you have to have that conversion. So the first 2 up here just showing conversion of nanometers to meters. That should be old hat at this point. And the reason why we have to do that is because the speed of light is 3.00 times 10 to the 8th meters per second. So your wavelength has to be in meters so that those units will cancel out or become unity. And then we have a number over seconds, which you should recognize that as frequency or hertz. And so once we have the frequency, we can plug it into Planck's equation and determine the amount of energy of a photon that was at a wavelength of 5.00 times 10 to the negative fifth meters. All right. So again, where did this come from? Let's go back. Let's make sure we're following along here. So we had 500 times 10 to the fourth nanometers, and we converted that to meters. That was the wavelength of A. All right, let's go back to just to show that again. 5,000 nanometers, or 50,000 nanometers, which is in the infrared region. All right, the last one, just to focus again. So we know that energy equals kinetic energy times the binding energy. So if we're going to solve for the kinetic energy, we get kinetic energy equals the energy of the photon minus the binding energy, and that's what we have right here. Now, this has already been calculated. You calculated this in part B. There it is. So we plug that in for h nu minus the energy of the binding energy, which is in electron volts that we converted to joules. Make sure these units are in agreement. Remember, they have to be in agreement. The other thing to remember is when you can do this on the calculator, but remember, before you add or subtract numbers, they have to have the same exponents. So you're probably going to change this one to 0.59 times, it's 0.59 times 10 to the negative 18th power. So you take a power of 10 off, move it over here to make this 10 to the negative 18th power. And so when you do that, the reason why that's important, you'll see your least significant figure lies in the tens place. That's why the final answer is known to the tens place. And so we get 3.2 times 10 to the negative 18th joules. So that's the kinetic energy required for the electron to travel from the collector plate to the, let's see, is that the emitter, and then to the collector plate. All right. So what we've done here is, again, let's not get lost in the forest here. Planck came up that energy is equal to h nu, which is a totally different physics altogether. He says that energy is quantized, that energy doesn't exist as a continuous from one point to the other, that it actually occurs in steps, and you jump up to steps or you jump back down through steps, but energy is quantized. Again, totally new physics. And the reason why this physics came about was classical physics could not describe the behavior of an electron or particles on the subatomic level. So Planck came up with this new physics, modern physics, quantum physics, to describe energy on the atomic scale. Most people thought he was off until Einstein proved that, yes, this equation can be used, and there are experiments to prove that this equation is valid in that this photoelectric effect problems that we see here. All right, so once Einstein says that, you know, there's these packets of light called photons, discrete packets, and that they give off a certain frequency, then we start investigating the atom. So let's look at the next slide here. So emission spectra, we knew before Planck that when we take an element and we heat it up in the gas phase, it does not show a continuous rainbow of wavelengths from red to ultraviolet, but that we actually see distinct bright lines in the visible part of the spectrum. So again, we're using the word light here. So we generate line spectra, and they're only at specific wavelengths and not a rainbow of colors. Now that's really big, because if it was a rainbow of colors, if every color was available from red to violet, that would indicate that energy is continuous and that we don't have these steps that Planck was talking about. So this is what I'm talking about. You have you take any element in the gas phase. You can use heat. A lot of times when in the lab we use, we'll take group 1A salts and put them in a flame, and then we look at the color given off. Well, we can also take any gaseous element, pass a high voltage current through it, and we get a discharge, a light, just like a light bulb, right? And so the light comes off, and we have a slit to culminate the beam. So we get a nice, we don't take all of the light, we take a column of light, and we pass that light through the prism. And remember how a prism works. The more wavelengths that pass through the glass, the more the light interacts with the glass and the more it bends. So that's why you see violet down here at the bottom. Red is longer wavelength, so it interacts with the glass less, and so we don't see the red light bend as much through the prism. And then we have a photographic plate to collect the line spectrum. All right. So when we heat hydrogen up, we get this line spectrum. We don't get a rainbow of colors. We get distinctive wavelengths. And remember, these distinctive wavelengths represent certain energy transitions. So energy is equal to h nu, and we can also say that energy is equal to hc over lambda. So because we're getting specific wavelengths, we're getting specific frequencies, we're getting specific energies. So what's so neat about this, this is a type of chemist I am. I'm a spectroscopist. So every element has its unique line spectrum. So each line spectrum, or spectra as looking at multiple ones, each line spectrum it's a fingerprint that identifies that element. So like lithium, I don't know if you've ever seen lithium burn or excited, but it's really crimson red. Well, that's why. That's the brightest band. It's in the crimson or red, red part of the spectrum. Sodium lights. Now you guys have seen this. You're driving down maybe the interstate and you notice that the overhead lighting is orange. That's because there's sodium lamps lighting up the roadway. And so because these are mostly in the yellowish orange region, that's why we see that color coming out of the lamp. Let's see, what else do you know that maybe? All right, neon. You've seen a true neon sign. It's real orange red. Look at all those bands here in the orange red region, and they're very bright. All right. In fact, a true neon sign, or a noble gas sign, is where we take different gases like neon and argon, and argon's going to be a blue or kind of a purple, kind of a purplish light. So by mixing, and then helium, another noble gas, it was going to look probably, I don't know, it looks kind of like maybe something in here. It's pretty bright in this area here. So each element has its own unique spectrum. And why would I need to know this? Well, this is how we do a lot of remote sensing. Like, let's say we've never been to Mars. What kind of elements are on Mars? Well, we can look at the reflection of the light from the sun from the surface of Mars and determine what elements are present based on these fingerprints here, these line spectrum. Neat stuff, it really is. All right, so after these line spectra, we have E equals h nu. We are talking about that energy is quantized, and now we're seeing that the photon's energy is also quantized. Johannes Rydberg came up with an equation that could calculate the spectral lines in hydrogen. So again, let's go back. Let's look at this. So hydrogen looks like this. Here's the line spectra. And so he comes up with a mathematical equation to explain these wavelengths. And this is what's really neat. So we're taking math to describe something that physically occurs. So he says that 1 over the wavelength is equal to Rydberg's constant, and then 1 over N1 and 1 over N2, where N2 is always greater than N1. So what he's saying is that for an emission spectra, that means we start at a higher N level and we fall to a lower N level. So N2 is here, N1 is here. The electron has to fall like so. And when it falls, it emits a certain wavelength or frequency of radiation. And we know that if we know the frequency or the wavelength of that radiation, we can use E equals h nu to determine that energy, or we can use E equals hc over lambda. So notice this is 1 over lambda here to ultimately determine the wavelength. Or, given the wavelength, we can determine the energy difference. So, Rydberg comes up with his constant is here. Yeah, that's not the best. I tried doing that with the mouse. It didn't work out so well. All right. So, that's Rydberg's constant. So, what I want you to know is I'm not asking you to memorize this equation. I'm not asking you to memorize Rydberg's constant. I do want you to be aware that N2 is always greater than N1. All right? That's important. Make sure you understand this part. And you're going to have calculations on this in your homework, and you're also going to have calculations in your quiz on this. But I'm not going to test you on this. I don't think it's that important. Why I think this is important is it shows a simple equation that describes a physical phenomena such as lines in a hydrogen atom. Those lines represent energy transitions. All right, so according to the law of classical physics, electron is moving from an orbit to an orbit, and that would radiate this electromagnetic radiation. So the downside is that if that's all that was going on, the electron being negatively charged and the nucleus being positively charged, the electron would eventually go into the nucleus and annihilate itself with a proton. So Bohr takes all this information that we've talked about, and he said, okay, I agree that energy is quantized. And he says that what we have here then is we have the nucleus. And then he says the electrons orbit the nucleus much like the planets orbit the sun. And so this is following, what we know about Planck's equation, that energy is quantized. The electron can exist here, it can exist in this orbit, or it can exist in this orbit, but it can't exist in between. And so an electron in any of these allowed orbits will not radiate energy and therefore not spiral into the nucleus. All right, so that's Bohr's argument that, okay, let me tell you why there's such a thing as line spectra. It's not that the atom looks like this, which is Rutherford's model, which has a positive nucleus and the electrons are just anywhere around the nucleus, but that the atom actually looks like this, where we have the nucleus and then with the positive charge, and then the electrons are in specific orbits, specific energies, quantized levels. And so everybody's like, oh wow, this looks great. So then Bohr takes the equation and here's what he comes up with. The energy of the n value, which orbit you're in, is equal to negative 2.18 times 10 to the negative 18th joules 1 over n squared. So whatever orbit you're in. And the orbits are always whole numbers. You're in the first orbit, the second orbit, or the third orbit. So the most negative value is n equals 1, and that can, and remember, here's something to remember. The more negative the value in energy, the more exothermic. We don't really know about that yet, but the more negative value, the lower the energy is. So we'll just say it that way. The more negative value, the lower the energy. So n equals 1, closest to, and again, what he's saying here, if I put a 1 in here, I get this value here. And that's the most negative this number is going to get. Because as this number increases, this overall fraction gets smaller, and this number is going to, and then when we multiply a smaller number times this, we're going to get a smaller number over here. So the most negative value, the most stable, is where we're at the lowest energy level, the lowest n value. All right. So anything where the electron and a hydrogen, and we're only focused on hydrogen here, so let me just stress that again. We are only talking about the hydrogen atom only. So anything where the electron is in a orbit greater than 1, we call that an excited state. The electron is not in its ground state, it's not in its lowest energy level, it's in an excited state. So the radius determines n equals 2, n equals 3, n equals 4. So again, what happens here, here's the nucleus, and then we have n equals 1, very close to the nucleus, then n equals 2, n equals 3. Now, as we get further and further, the orbits do get closer together. All right, let me just say that the biggest step is like if this is n equals 1, oops, let's go back. Let me see if I can do that. Well, we'll show it on the next slide. So this is, and maybe this is what you think the atom looks like. You know, I asked you to draw a picture of the atom at the beginning of this chapter. I said, draw a picture of what you think the atom looks like. If you draw the planetary model, the Bohr model, where you show the nucleus and then each one of those circles represent an orbit, then you're thinking about the Bohr atom, the Bohr theory. So here's another way to think of it. Let's say that this is n equals 1, and I think really probably what the author intended here. Let's see. You know, I really, yeah, maybe this is 1 down here, and this is 2. This is 3, 4, 5, 6. So what I want you to get out of this, the biggest jump is between 1 and 2, and then 2 and 3. Notice as we get further from the nucleus, where the nucleus is, which is down here somewhere, the closer the orbits get together. The energy starts to look, can you imagine at some point the steps are so small in increment that they start to look continuous? That's where we're getting with this. All right. So what you notice is this is emission. The electron should normally reside here. Here it's in level 3, and so when it falls from level 3, from an excited state, level 3 to level 1, it's going to emit a certain wavelength of radiation. And then we could have a transition from level 5 to 4, and that's going to emit a lower wavelength of radiation because there's not as much energy difference between 5 and 4 versus 3 and 1. So the change in energy, where we started initially, where we finish up, that's going to be a negative value, right? Because this is, let's say this is n equals 1. And this, or this is n equals 1, and then this is n equals 4 initially. So 1 minus 4 will give us a negative value in energy, which means exothermic, gives off that energy. So Bohr takes his equation and he sets one equal to n initial and the other one to n final. And when we solve for this equation, we get this equation here. And this is Bohr's equation. So this is like similar to Rydberg's equation. In fact, they are related. Bohr is focused only on the hydrogen atom, and the Bohr constant here, the negative 2.18 times 10 to the negative 18th, that's going to be related to how much energy it takes to remove an electron from an atom, the ionization energy. So again, not asking you to memorize this, just asking you to be able to plug in the n values and solve for the change in energy, or given the change in energy, determine what these n values will be. So I talked about this in the announcement. Each one of the energy transitions has its own name. So the way we determine the name of the series of energy transitions, if the final resting spot of the electron is in the first energy level, n equals 1, then we call it the Lyman series. If the final resting point of the electron is in the second orbit or second energy level, we call it the Balmer series. This is the most important one because this is the one that's in the visible region. So make sure you know the Balmer one. This one comes up. This is how, I mean, the Balmer is what we used the most initially because that's what we could see with the eye. And then Paschen and Brackett, these transitions are really that n equals 3, n equals 4 is the resting spot. So you know, n equals 3 to 4, that's not much of a transition. Let's go back to that previous slide. Well, let's go to the next slide and you'll see what I'm talking about. So here is an example of the transitions. Notice these are huge. To jump from 1 to 2 is a huge jump. So these are going to have the most energy. That's why these are in the ultraviolet region. All right, so if we fall from 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1, they're all huge transitions. And these huge falls represent large differences in energy, and so we're going to get higher wavelength or higher frequency, shorter wavelengths in the ultraviolet region. Now, in the second series, the electrons are falling from higher energy levels, but they end at n equals 2. And notice all of these transitions are correspondingly shorter than these transitions. So because the energy difference is less, then less energy, higher frequency in the visible region, longer wavelengths. And then these transitions are even less, and these are even less, and so that's why these are in the infrared region. Less of a energy transition, less energy, lower frequency, longer wavelength. And here's the other thing I want to point out. Again, the first big 2 or 3 or 4 jumps is, you know, they're large. 1 and 2, the first 2 to 1, 1 to 2, or 2 to 1 either way. These are emission spectra, so this is really going from 2 to 1. Notice how big this is. And then 3 to 2 is a little less, and 4 to 3 is a little less. Notice as we would go from 7 to infinity, they finally get to the point that the lines are so close together we call it a continuum. So those are the things I want you to pick up about the Bohr theory. It is a transitory period in atomic theory, and the calculations are important, but I'm not asking you to memorize them, and I'm not asking you to memorize the constants. But I want you to understand what's going on here. We are taking an electron, we're exciting it to a higher energy level. This is an excited state. When it falls back down to a lower energy level, and when that happens, a certain frequency of radiation is released, which represents also a certain wavelength, and that's how we can determine the amount of energy between these two levels. So that'll be delta E. And people like this theory because now, again, it changes what the atom looks like. Now the atom has a nucleus. Now the electrons orbit the nucleus, much like the planets orbit the sun. And people thought that was going to be a great model. So a calculation, it says calculate the wavelength of a photon emitted from when we go from a transition from n equals 4 to n equals 2. Now here's something I do want you to pick up on. For it to be an emission, we have to fall from a higher energy level to a lower energy level. All right? If we went from n equals 2 to n equals 4, you would have to put energy into the electron. That would be called an absorption spectra. But emission means the electron is falling from higher energy level to lower energy level, and it's going to emit that much energy. It's just like when you fall off a ladder. The higher you climb up the ladder, the worse it hurts when you fall off because you release more energy. Same thing here. So because we're going from n equals 4 to n equals 2, the electron is going to emit energy. If it emits energy, it has a certain frequency, and it also has a particular wavelength. So here's how we do this. You're going to use this equation. I'm not asking you to memorize it, but here is Bohr. Actually, it's kind of funny. I mean, it is, so this is Bohr's equation, but what they've done here is, remember, E equals hc over lambda. So they left the 1 over lambda here, and they're divided by hc here. And so then we have 1 over the final level minus 1 over n squared of the initial level. Okay? So Planck's constant, you're going to have that memorized. You're going to have the speed of light memorized. And the final is the lower energy level, and the initial is the higher energy level. That's got to be the case if it's emission. And then let's watch the units here. This joule and this joule cancel out. This second and this second cancel out. And so when we multiply make sure you use the parentheses, and parentheses 1 over, I would say it this way. I would say 2 squared, and I'd hit the x to the minus 1 key on the calculator, minus 4 squared, hit the x to the minus 1 key on the calculator. So I would actually do it that way. That'd be the easiest way. Parenthesis, 2 squared, x to the minus 1 key, minus 4 squared, x to the minus 1 key. Get this, and then multiply this out, and you should get this for an answer. And notice the units, meters to the negative 1 power. Now, most of the time, we would want that in meters, so you might want to do the reciprocal of this, x to the minus 1 key, and that would give you your answer in wavelength. All right? So you could do that instead of leaving it as what this is solving for. So be careful. Sometimes they're asking you to solve 1 over the wavelength. Other times they're asking you to solve for the wavelength. All right. So there was a problem with Bohr's theory. People were asking, well, when you look at the Bohr model, why do the electrons have to be in specific orbits? Like, what determines the distance between these two orbits? And other problems with the Bohr model were it only worked for one electron systems. He could only do the calculation for a one electron system, a hydrogen-like atom. Anything with more than one electron, Bohr's theory is not working right. It's not correctly determining the wavelengths. So de Broglie tried to help Bohr out. He said, okay, I can tell you why this orbit is allowed and this orbit's allowed, but nothing in between's allowed. He said, an electron can behave like a wave and a particle. And so he talks about when you pluck a string, you have places where you get a vibration. So let's look at it. When you pluck a string, the simplest is like this, where the string just waves up and down like this. And you've seen this probably on a guitar or something like this. So this is a node. This is where the electron cannot exist. That's a node. And the electron can't exist here because that's a node. So this vibration is where the electron energy can exist. And it can exist at the ends there. So then, that's the simplest of vibrations. Let's look at some more. They got a better picture of this on the next page. So this is the simplest. So here we have 1 times a half wavelength. That's not a full wavelength, right? Remember, a full wavelength is a complete cycle. So it's like this. Or if we're measuring from peak to peak, you start at a peak, you go down to the trough and back up like that. So this is 1/2 wavelength. This is a full wavelength. So notice what we have here. The length is 2 times the half wavelength divided by 2. All right, so n equals 2, we get a full wavelength. N equals 3, we get 1.5 wavelength. So we get 3/2 wavelength. So de Broglie says the only vibrations that are allowed are in a whole number times half of the wavelength. So if the wavelengths can connect, let's look over here, and if they can vibrate where they connect, then this particular average energy is allowed. So this is this here, the average energy. And if, as long as they can vibrate and the wave completely, each half wavelength completely connects with another half wavelength, then this particular energy is allowed. But when the wavelengths, the half wavelengths, do not connect, this particular energy is not allowed. It's not allowed because it's not forming a complete half wavelength. So that's why de Broglie saying, okay, Bohr's right. Look, you've got the atom, and then the electrons are in this orbit, or they're in this orbit, and these are the first 2 orbits that give you a complete number of half wavelengths. But anything between here and here and here and here, there is no half wavelength. So there's an equation for that. So here it is. The allowed transitions are 2 pi r, the circumference of the orbit or circle, times a whole number of wavelengths. All right. Works very well, but it only works for hydrogen-like atoms generally. Now, what's so cool about this is de Broglie is the first to really give us a mathematical equation to bridge the debate between particle, which has mass, and wavelength, which is dealing with waves. So because only certain R values are allowed, that means only certain sizes are allowed, certain energies, we can show the relationship between wavelength and mass. So here's wavelength, here's the mass, here's Planck's constant, and there is the velocity of the particle. And you go, well, what does this do for me? Well, it's saying that here's a mathematical equation that describes a particle in that it has mass and it has velocity, and that it has also wave-like properties. So this is a really cool equation. It is a hypothesis. It's not a theory. It's not a law. It's something that de Broglie came up with to show that relationship. Okay, so it's called the de Broglie wavelength. So every particle, whether it's an electron, a baseball, a bullet, they have a de Broglie wavelength. So here is an example. You got a 25-gram bullet traveling at 612 meters per second, and you have an electron. This is how many kilograms the electron weighs, traveling at 63 meters per second. For both of these objects, we can determine the de Broglie wavelength. Now, the most important thing on this slide is probably this right here. This is the relationship between what a joule is broken down. It's kilograms meter squared per second squared. And this is going to become important multiple times in this semester and Chem 180 and physics. So you may want to memorize that. That one comes up so much, I think it's important to know that one. All right. So what this does, we go from an energy unit to a mass and then velocity of our acceleration unit. So keep that in mind. So I'm not asking you to memorize the equation. Yes, I do want you to know Planck's constant. I do want you to know this mass has to be in kilograms. There's the velocity. But you're really pretty much given the problem, you just plug in the values and solve for the wavelength. Or given the wavelength, you could go back and determine the mass. That's generally what you do, or the velocity. So again, not asking you to memorize the equation. I am asking you to watch your units and plug in the numbers correctly and watch your units. That's what I'm asking for here. I'm not asking you to memorize it, though. Again, I think it's a transitory period. All right, so there's a series of experiments, 1920s and so forth. We start seeing electrons do possess wave-like properties. So we're still particle in a wave. And this is how we determine, by directing a beam of electrons, which are most definitely particles. We think of an electron as a particle. You probably thought of it was a particle because we've shown it as being this particle striking the phosphorus plate. But electrons, through a thin piece of gold foil, Thomson obtained a set of concentric rings, similar to the diffraction pattern observed when X-rays, which are most definitely waves, are used. So what this is saying is that he sees the atom, the nucleus, and then he sees a series of concentric rings here. So if it's a ring and the electron has wave-like properties, then we can start looking at mathematical equations that describe wave mechanics. All right? So any wave that we see, whether it's this, or it could be some real crazy wave like this, and it could be pointed, or it could be a square wave like that. Any wave has a mathematical equation to describe that wave. So Schrodinger and Heisenbeg start trying to explain the behavior, the wave-like properties of an electron using mathematical equations. All right, so we start now investigating the electron in an atom with its wave-like properties using mathematical equations called wave functions. All right, so let's talk about the uncertainty principle. So Werner Heisenberg started using mathematical equations to work with the electrons, to describe the functionality of the electron. So what I mean by this is that if an electron behaves like a wave, and it doesn't matter whether it's that type of wave, or maybe it's a square wave, or it's something that looks like this, every wave can be calculated into a mathematical function, or it can be made into a mathematical function. So Heisenberg was trying to describe the electron according to its wave-like properties, and he starts making a mathematical equation of this, and he determines that the position and the momentum of the wave is greater than or equal to Planck's constant divided by 4 pi. All right, so you say, what does that mean? Well, that means that momentum, which is mass times the change in velocity, or the uncertainty in the velocity. So the position times the mass of the particle, in this case the electron, times its variation in velocity is greater than Planck's constant divided by 4 pi. Now here's where it really comes in here. Making a measurement of the velocity of the particle more precise means the position must become correspondingly less precise. So if you make this more precise, this has to be less precise because this has to hold that the product of those things have to be greater than or equal to h over 4 pi. Or if you know the position, then the velocity has to have greater variation. So let's look at a problem that kind of drives this home here. So an electron in a hydrogen atom is known to have a velocity of 5 times 10 to the 6 meters per second, plus or minus 1%. Using the uncertainty principle, calculate the minimum uncertainty in the position of the electron given that the diameter of the hydrogen atom is less than 1 angstrom. All right? Comment on the magnitude of this uncertainty. So we know what the mass of an electron is. I don't expect you to have that memorized, but we've talked about the mass in chapter 2. We do know Planck's constant, and I do expect you to have that memorized. All right, let me erase this, and then we'll come back and start filling it in here. All right, so the variation in velocity, they said was, let's go back, variation in velocity, they said was 1%. All right, variation in velocity is equal to 1% times the speed of the electron. So that's a pretty large variation, 5 times 10 to the 4th meters per second. All right, so if we take Heisenberg's equation and we solve for position, the variation in position of the electron in relation to the nucleus, we have h, Planck's constant, divided by 4 pi, divided by the mass times the variation in velocity, which we just calculated. That goes right there. So we plug this in. Planck's constant divided by 4 pi divided by the mass in kilograms. Why is this in kilograms? Because this is in kilograms up here. Remember, it's joules, and we got to keep our units of the same value. So those are both kilograms times the variation in velocity. Well, when we calculate this out, this has to be greater than or equal to 1 times 10 to the negative 9th meters. All right, we just said that the atom, that the atom is 1 times 10 to the negative 10th meters. That's what an angstrom is. So if you look at these two values, this value, 1 times 10 to the negative 9th meters, which is 10 angstroms, 10 angstroms, which is 10 times greater than 1 angstrom. So what this is saying is the uncertainty of the electron's position is 10 times larger than the atom. So you could say, here's where the nucleus is, and then you could say, this is the size of the atom, and then somewhere out here is the probability of where the electron is. 10 times larger than this. So it's really way out here somewhere, right? 10 times. So Heisenberg states that the electron, you cannot know its position and momentum, or its position and its velocity. So you're going, well, what does that do to the atom? Well, why I'm stressing this, we've just deconstructed Bohr's theory. So Bohr said the electrons orbit the nucleus much like the planets orbit the sun. Well, if the electrons orbit the nucleus like the planets orbit the sun, I can determine its trajectory. I can tell which way, I can look at it here and go, it's going to follow this exact path. And then I can wait for it to come back around, and then I know how long the path is, so I would know its position and momentum at the same time. But Heisenberg just said you cannot know the position and momentum of the electron at the same time. So, atomic theory is about to change dramatically. So along comes Erwin Schrodinger. Schrodinger is doing more mathematical functions to explain these waves. And they're very complex. And again, think about this. He's doing this without a computer. He's doing this without a computer. He starts writing equations that describe the behavior of the electrons. And these equations require advanced calculus to solve. They are very complex. But know that these equations incorporate the particle behavior, the mass, the wave behavior in terms of a wave function. This is what I want you to know, wave function. This is a mathematical equation to describe the behavior of the electron, wave function. And you probably should know this symbol here, psi. That is what we usually use to represent the symbol for the wave function. Now, what's interesting about psi is when we square the wave function, we get the probability of where the electron is located in relation to the nucleus. And that's really important. Squaring the wave function gives us the probability of where the electron is located in the atom. So, Schrodinger, working with these wave functions, which are very, very complex, he finds that there are 4 variables that will tell us where the electron is 90% of the time. That's all we can do. That's the best we can do, right? We cannot know position and speed or momentum of the electron, but if I know it where it is 90% of the time, I'm going to be okay. So he comes up with quantum numbers, a set of quantum numbers that will describe where the electron is in relation to the nucleus. So here's what wave function squared looks like. We get a paint spray diagram. That's what this is called. And where the paint is darker, that is a higher probability of finding the electron. But notice it fades away, but it never really goes to nothing. So since we're interested in knowing where the electron is 90% of the time, we're fine with that. We generally draw a ring around where the 90% probability is, something like this. Now, that is not an orbit. I want to stress this. This is really important. It's not an orbit. We're not saying that the electron is right here on this ring going around and around like Bohr's theory. We're saying the electron is somewhere in this volume 90% of the time, and the other 10% of the time it's out here somewhere. All right? So even though you see rings maybe around an atom, that doesn't mean they're orbits. It could be their probability rings. All right? And so if we're talking about the most modern theory of the atom, these lines represent, this circle represents the probability of where the electron is located. So because they're not rigid orbits, like Bohr's theory, we call them atomic orbitals. Know the difference between an orbital and an orbit. An orbital comes about by a wave function, and the probability of that wave function gives us, or the square of that wave function gives us the probability of where the electron is located. All right? So here's the topic on the 4 quantum numbers. And this will be the last thing I talk about, and then it picks up with what you see with the other videos in the last announcement. So Schrodinger says there's 4 quantum numbers that tell us where the electron is 90% of the time. They are N, the principal quantum number, that's related to energy and how far the electron is from the nucleus. The further the electron is from the nucleus, the higher the N value, the more energy the electron has. L is called the angular momentum quantum number. It shows us what, it's kind of like if you thought the electron was attached to a string and you were spinning it around your body, where can the electron go? Where will it be 90% of the time? So we're going to get some probability shapes that are different than just a sphere with the angular momentum quantum numbers. The magnetic quantum number, the word magnetic means we've put the atom into a magnetic field, and it causes splitting to occur, and we start to see orientations, different orientations of where the electron is in relation to the nucleus. And then the last quantum number is the electron itself spinning clockwise in a magnetic field or counterclockwise in a magnetic field? And so that's called the spin quantum number. So these 4 quantum numbers, let me just kind of explain what this is like. If I want to find you in the United States, I say, what state are you in? Kentucky. I say, what county you're in? Fayette County. I find what street you live on, and then I find your house number. So those 4 things, that's 4 things that tell me where you are, most likely located. Are you there all the time? No, you're not. So just like your home address, you're not there all the time. Maybe you're there, probably not 90%, but you're there a certain percentage of the time. So these 4 quantum numbers, N, L, ML, and MS, give us a probability of where the electron is in relation to the nucleus. So N, again, starts with the value of 1 and increases. N1 is closest to the nucleus, and as the N increases, we're getting further and further from the nucleus, and the energy of the electron is increasing. These also correspond to the periods on the periodic table. So the first horizontal row on the table is called a period, and so hydrogen's electrons are in period 1, in the first shell around the nucleus. When we drop down to lithium, the first element in period 2, its electron is in the second period, and it's in the second shell. It's the first electron that's placed in the second shell around the nucleus. Now, notice I'm calling them shells, not orbits. So the shells are the energy level. So if somebody says shell or energy level, they're talking about this, shell or energy level. So you got to know that you got to speak the language. So we call these shells or energy levels. All right. The next value is L, and L is a whole number, and it's related to N. You always had the value of L equal to 0, and then any whole number up to N minus 1. So what I'm saying here is this: if N equals 4, so we're in the 4th energy level, the possible L values are 4 minus 1, which would be 3. You must always have 0. And then what are the whole numbers between 3 and 0? Well, there's a 2 and there's a 1. So if N equals 4, the principal quantum number equals 4, the 4 angular momentum quantum numbers are 3, 2, 1, and 0. Now, each one of these L values has a letter designation. So L equals 0 is S, L equals 1 is P, L equals 2 is D, L equals 3 is F, L equals 4 is G, and then it goes like the alphabet. All right? So L gives us, let me tell you what it's like. It's kind of like an apartment building. If you're on the first floor, there's only one room. So this is N equals 1, and this is L equals 0. If you're on the second floor, N equals 2, so we're further from the nucleus. The nucleus is down here. N equals 2, you get 2 L values. You get L equals 2 minus 1, which is 1, and you also get 0. And then if you have N equals 3, you get 3 L values. You get 3 minus 1 is 2, and then you get 1 and 0. You always have a 0. All right? So this picks up where those other videos start. So I'm not going to reinvent the wheel here. I'm going to stop here. But it's important that you understand the relationship between N, L, ML, and MS. It's important that you know terms like off-ball principle, Hund's rule, Pauli exclusion principle, that's a big one. Pauli exclusion principle, all right, which says no two electrons can have the exact same 4 quantum numbers in an atom. They can have the same 3, but they can't have the same 4. And it's not just memorizing that definition. You need to be able to apply it. So if I give you a string of quantum numbers, you can tell me which ones are allowed and which ones are not allowed. All right? Off-ball principle, Hund's rule, Pauli exclusion. Those are some of the rules that you should learn in Chapter 6. I hope this helps. If not, just email me. Be glad to develop other videos or discuss with you what parts of this you're not understanding. Thank you.